Thanks for coming to today's Sonic and SAI session. Each talk, the first two talks are 25 minutes. We will raise a sign whenever 10 minutes or 5 minutes left. Then we have 4 small sessions on monitoring. Each one is 15 minutes. With that, I will give time to Guohan and Jay.
Good morning, everyone. Thanks for coming early. The first engineering session on Friday. I'm Guohan from Microsoft. So today I'm going to talk about the SAI update on behalf of the SAI communities. So there's a lot of good work has went to the SAI in the last year. So I'm here to just update on behalf of the communities. So before I give update, I want to first spend a little bit time to describe what is the SAI and how the SAI works. So SAI is a switch abstraction interface. It is a set of APIs that is used to control the switching ASICs. So we have so many different ASICs. Each ASICs have their own SDKs. The idea is to have a unified control interface, allowed us to control different ASICs using the same set of APIs. The SAI interface is basically a CRUD operations over extensible entity attribute value data model. I'll describe the data model in the next slide. And also the SAI defines a reference data plan behavior model, which defines when the packet gets into the ASIC, how it is processed. In the first step, it gets processed by the port, then by the lag, by the router. It defines a reference data model, how the packet gets processed in the ASICs. So starting from 2014, when the SAI first introduced, we get significant feature and partner growth around these SAI communities. So here, I'm going to describe a little bit about the SAI APIs and objects. So basically, the SAI has 4 sets of APIs and many more objects. The API is simple. It only has 4 kinds of APIs: a create API, the remove API, and the set and get APIs, which allows you to create an object, delete an object, and then set attribute on the objects, or get attribute from the objects. So for example, if you look at the right side of the box, there is an example object. So object has a key, which is object ID. When you create the object, you get the object ID. And inside the object, it's just a set of attributes. If you look at below, there is a typical example object called the next hop. In this case, when you create the next hop, you get object ID, which is 0001. And then when you try to create the object, you supply a set of attributes. In this case, you will supply the IP address of the next hop and the next hop type. And then once you call the create API, it will give you an object ID. And later, you can use that object ID to set and get and to remove. So this is basically how SAI object and API works. So we talk about the behavior model. So when the packet gets into the ASICs, the SAI defines a set of phrases or stages that how the packet gets processed. If you look at the bottom, there's a blue boxes. And so that defines basically the pipeline model. So when the packets first came in, it processed by a port. And then if it's then there is a route interface to determine whether the packet is getting forwarded by layer 3 or the layer 2. If it's forwarded by layer 3, in process by a route object, and then the route object pointing to a next hop, and then the next hop point to a neighbor, and then to another route interface, which packet gets sent out from another route interface, and then to a port. So each stage represents a SAI object, and we define those APIs to create a corresponding object in each stages, so we can define how packet is processed in the pipeline. There are 4 main categories of the SAI APIs. The first one is the monitoring. So we're going to introduce the TAM proposal with the telemetry and monitoring from the Broadcom. We also have a set of other monitoring style objects such as microburst, critical resource monitoring, and the int. Then the second category is the protocol support. So we define how the different packets can be processed by the ASICs. We support MPS, the .21BR, the segment routing, and the basic layer 2, layer 3 for links. And then we have also another set of SAI object to provide the reliabilities and quality of service in the ASICs, such as L3 fast reroute, the BFDs, and the ECNs. And then the last category is a set of infrastructures for the people to extend the SAI. For example, we have this, the contribution, the P4, SAI P4 model from Manox can define the behavior model that we have just described. And also there are other set of the multi-MPU support, and we can also provide the capability query APIs, which allows the user to query what is the ASIC capabilities. And the last one is we also allowed users to define their own extension APIs through the SAI so they can have their own vendor-specific features. Yeah, so here we have a lot of ASIC support from SAI. And the next one, I'm going to invite Jay Kumar from Broadcom to discuss a TAM proposal.
Yeah. Thank you, Guohan. Good morning, folks. So I will talk about the work which has been done last year regarding telemetry and monitoring. And although it says it's a Broadcom proposal, but by no means it is. It's a community effort, and there are a lot of folks which were involved in this. So this is a brief update. Feel free to ask questions if you have. So I'm just going to go over the contributors who all worked on it, what the use cases we are trying to solve, and a very high-level architecture. And then briefly, what are the next steps we are working on. So I just want to acknowledge the folks which have been extensively contributing to this. They have participated in terms of discussions, offline discussions. Let me see who is here. Hui is here, Nikos, Vitali, Giri, Ashok, Mike. I know Mickey is here. Okay. So that's and I'm pretty sure there must be a few more folks which I might have skipped, so I apologize for that, but this is just some set of folks who are actively participating. This is a very high-level use cases which we initially focused on. The very first use case was that we wanted to create a streaming interface. As you know, the pull model of the data within the NOS typically does not scale given the scale of switches we have today and the amount of information is there in the pipeline. So for that reason, we wanted to create a generalized push model, and that's the streaming telemetry interface we wanted to define. And then since we are defining the streaming interface, we wanted to also use this opportunity to define some hierarchical analytics, some mathematical model, which gives us ability to do local pre-processing of the data and then send some summary of the data to the collector. And this also creates foundation for our next step, which is machine learning. As you know, that there is an effort to do either inference logic or some kind of machine learning in the chips. And this gives us a very rudimentary basic framework where we can add not just the basic mean mode or running averages kind of mathematical function, but a little bit more advanced mathematical functions which are actually implemented in hardware. So the basic framework has been defined. Besides that, one of the efforts we wanted to do is to create a consistent data model. And this is for internal consumption and external consumption. And by that, I mean, today, let's say if you want to query a show command, and any consumer of that show command has to literally do the parsing of the screen scraping, to make a meaning out of the data. And the effort here is to define a consistent data model which can be used internally by the daemons which are running on the operating system, or it can be consumed by the collector, which might be running inside the Sonic or it's running outside the Sonic. And the advantage of doing that is once the API is defined to get the data, then the deserialization of the data is done by the auto-generated stub functions. So typically, you don't want to go and write the deserialization function or the interpretation function for the data. So there is some effort which has been defined for the data encoding. We have taken a stance that the generalized data encoding is going to be a protocol buffers, Google protocol buffers. But the APIs are extensible. You can define custom data model if you feel like, or Thrift and JSON are also supported. And then the ability to transport the data on transport, this is very important. So today, Sonic is more of a 1RU kind of architecture where everything is localized. But when you have a chassis, the data need to be carried over to the supervisor or to the route engine, or it need to be carried to an external collector. So in that case, you do need a certain kind of transport, preferably standardized transport. Sometimes there are proprietary implementation. So these are the use cases which we were addressing in the TAM. And whatever I am talking, except for the machine learning part, has been implemented in the API. So this is a very high-level architecture. The approach is that the objects need to be created in a very generic fashion. They are chip agnostic. We do not want to create chip-specific objects. We abstract everything out in a generalized object, and then it is up to the chip vendor to make sure that those generalized objects are applicable to the chip functions. And if there is a need to define a new object, there is always the ability to define a new object. But that's the very basic idea. So we have very generic TAM object. The reporting objects are also generalized. So report format may use a serialization function, protobuf, JSON, and so forth. And it all depends on what the chip is supporting. Similarly, the event framework is present, which is, again, a generalized event framework. And then, as I talked before, there is some analytics function which we have provided, which can be extended based on the chip functions. So this is a very high-level architecture. And if you see in this, there is another function, which is the data can be sent out to an external collector, or the same data can be consumed by the NOS having a local collector. So same function from the chip should be able to work, whether data is being pushed out to an external entity or to a local entity. So that's a key point. So once in a SAI driver I implement a push of the data, then I really don't care. I, as in the chip vendor, does not care that SAI driver is sending the data to the local collector or to an external collector. So that's a key point here. This is just a diagram that how a TAM object is a single unified object. So in this, if you see, there are various port statistics, where are event definitions, and then the collector definitions. They kind of come together as a binded object, and everything is sitting under TAM object, and then TAM object is binded to a different other port objects or VLAN objects or queue objects. And then the SAI driver, there is a little bit of implicit processing here, if you see, that there are some objects which may not be applicable to the binded object, but that is to be taken care of by the driver. And that flexibility is very deliberate. We have kept it not a very strict binding function. So we have kept it as a loose binding function. And the next steps, right now, the pull request, which contains the basic telemetry and monitoring architecture, that's committed. I believe, Guohan, you have committed that to the main line. And there is a next pull request, which is open for review, where we are working on the, myself and Mickey, we are working on the INT APIs, which will define the various flavors of INT. And that is pretty much it from my side. Any questions? Yes.
Why did you use something like GNMI and extend it? Why did you create your own?
So let me repeat the question. Why didn't you use JMON? Oh, GNMI. Okay. So right. So GNMI is basically a sonic function, which is the subscription from a sonic or a consumption from a NOS point of view. Underneath, GNMI uses gRPC, which is the transport. gRPC defines the data model, which is using OpenConfig, and that is very control plane function. That's a very high-level function. This is to support that. In fact, if you remember, I did mention that protocol could be gRPC, right? So you can actually support the same GNMI config semantics down to the chip, if chip is capable. And then you can export the same data on a gRPC interface to GNMI. So you can, it's not a new, it's a complementary. It's a lower level function. Yeah. Okay.
Thank you, Jay. So next, I'm going to give some other updates in the SAI. So we have also support the PTP from the SAI perspectives. So the PTP is used for the time synchronization among the switches and routers through the network. With the PTP, once the time is synchronized among those switches and the servers, then we can actually use that to debug the packet and latency issues that we've been seeing in our network. So from the ASIC perspective, to support the PTPs, we need two main functions. One is be able to do the hardware timestamping for the TX and RX packet. The other one is to be able to adjust the hardware clock, for example, the offset and the frequencies, so I can actually provide the correct timestamping on the packet. And on the SAI interface perspectives, so we define the traps to allow us to enable the PTP on the ASICs and then also get the timestamp that the hardware timestamp from the ASICs. So here next, I'm going to describe how the PTP works in the context of the SAI and the NORS. So, so here we have a user space, a kernel space, and hardware. So on the user space, we're running a software PTP stack. So the first step for the PTP stack to do is to call the SAI APIs to enable the PTP timestamping functions through the SAI. Then after that, we were able to integrate the PTP stack with the Linux functionalities. So when the PTP stack is running, it tries to exchange the protocols with the PTP peers. Here, it sends a PTP protocol packet through the NetDev drivers. And then once the packet is sent through the ASIC will do the hardware timestamp on the packet. And then the next step of the PTP stack is to query the TX packet, the timestamp of the TX packet. So here, it calls the receive API to receive the timestamp of the transmitted packet. And then when you receive the PTP protocol from the other peer, the packet is coming with the PTP timestamps. So here, it will automatically extract the timestamp from the packet. So then, after the PTP stack exchanges the protocol with the peers, it calculates the correct timestamp, the hardware timestamp for itself. Then it tries to talk to the clock drivers in the Linux to set and correct the time frequencies on the hardware clock. Here, then the hardware clock will input the correct timestamp into the ASIC, so the ASIC will be synchronized through the PTP protocol. So overall, what we actually did on the SAI part is to enable the PTP timestamping. And then all other functions, we use the Linux APIs to do that. So that's how we can integrate the PTP with the ASIC without adding much functions in the SAI. So the third update is that we spent times to add our PTF test so that we can validate the SAI implementations. So for most of the time, each vendors have their own SAI tests to validate their own implementations. And as a community, we think we can do better if we maintain a common set of tests to validate because all the SAI has the same APIs, so we can actually have a unified way to validate all the SAI implementations. Here, we have a framework called the PTF Test. So the idea of a PTF test is simple. It first calls the SAI APIs to configure the ASIC. And then once the ASIC is configured, it sends a packet to validate whether the ASIC is forwarding the packet correctly or not. So for example, here we have a switch that connected to the host using 2 ports. So the PTF test works like first we call the SAI APIs to add a layer 2 interface in the switching ASIC, the forwarding interface. Then from the host side, we send a packet with a destination match to match that layer 2 interface. So then if the layer 2 interface is configured correctly in the ASIC, then the ASIC will see the packet and forward the packet correctly to another port. Then the host will be able to receive the packet and verify the packet. If the host, on the PTF side, on the host, we capture the packet and check if the packet is received or not. If the packet is received, then it means the layer 2 interface has been configured correctly in the ASIC. Otherwise, you wouldn't be able to forward the packet to the correct port. If it doesn't see the packet, that means the layer 2 interface is not in the ASIC. Then we have a problem. So using this idea, we can actually just call the SAI API, send the packet, and validate the implementation of the SAI. And this can be extended across different SAI implementations. So in the last year, the community is able to add 18 test cases around the layer 2, layer 3, ECMP, neighbor, and echoes. So altogether, we have 82 test cases, mostly focusing on layer 2, layer 3, host interface, echo, mirror, and the tunnels. So the next steps is for the called participations. So we talked to a few our partners in the SAI communities, identify some new areas that the partners are interested in. For example, the IFA, the NAT. We'd also like to use the SAI to control the external file and MACsec. These are the areas that we found that there's the interest around those areas. So we'd like to call the participation to define those specs in the SAI in the coming year. And we also want to add more community tests, the PTF test, to improve our test coverage over the SAI. I think, yeah, so that is all from our side. Any questions?
One question for the strict kind of treatment. I see
Sorry. Yeah, that's a good question. So it depends on the chip's ability. If chip is having an embedded controller, then chip can stream it out directly from the chip itself. Otherwise, the next option is the SAI driver. The data is not exported from the control plane.
But either way, it all happens under SAI, right?
It all happens at the SAI, yes. So the control plane will export the data, which is a control plane data. This is a data plane data, either going out from the chip or from the SAI.
I see. So my question is more coming from the, as you know, I'm working on warm boot, so lots of my thoughts is around there. So during the time when doing the warm reboot, the control plane is away. So we also want the capability of monitoring the chip status during this period of time. Then the only option is that we have this data coming out from the data plane, one of the data ports. Is that even possible?
Yeah, so data is coming out from a punt path from a CPU port if it's going to the host, to the control plane, right? Not from the front panel. And if that port is not available during warm boot, then you're right, the data cannot be exported.
Is there a way or source for those data to come directly out of one of the front panel ports?
We can do front panel port too, but if the data need to go to a local control plane, then what's the point of sending it out on the front panel?
Yeah, but you also have a diagram of sending data to a remote collector.
Yes, you can do that, yes, yeah. And that will keep on happening even during warm boot, because typically the embedded controllers are alive that time.
Okay, thanks.
Okay, if there is no more questions, let's go to the next one. Yeah, thank you.